Einstein was right about everything, except when he was catastrophically wrong. In 1935, Albert Einstein wrote a paper that he believed would destroy quantum mechanics. He called quantum entanglement spooky action at a distance and declared it impossible. The universe, he said, must be local and real. Objects must have definite properties whether you look at them or not, and nothing can influence anything faster than light. He was so confident that he essentially said if quantum mechanics predicts this nonsense, quantum mechanics must be incomplete. Then, in 1964, a physicist named John Bell proved that you could test Einstein's claim, and when the experiments were done, Einstein's intuition, the intuition that feels so obviously correct, turned out to be wrong. The universe is not locally real, and once you understand what that means, your entire sense of reality collapses. Let me show you how deep this goes. Imagine you have two coins, magic coins. You flip them in separate rooms, one in New York, one in Tokyo, and every single time, no matter when you flip them, they land on opposite sides. One heads, one tails, always. How is this possible? Option 1, the coins are communicating. When one lands heads, it sends a signal to the other, land tails. But that signal would have to travel faster than light, impossible. Option 2, the coins decided beforehand, before you flip them, they secretly coordinated. One coin knows it will be heads, the other knows it will be tails. No communication needed during the flip, the outcome was predetermined. Einstein chose option 2. He called these predetermined instructions hidden variables. The coins or particles carry instructions that determine their behavior. You just can't see these instructions until you measure. This was the EPR paradox, named after Einstein, Podolsky, and Rosen. They argued that quantum mechanics was incomplete because it didn't account for these hidden variables. And here's the thing, it sounds reasonable, it feels right. Objects should have properties whether you look at them or not. A coin is either heads or tails before you check. Reality shouldn't depend on observation. But quantum mechanics said otherwise, and in his lectures compiled in The Character of Physical Law, Feynman explained why Einstein's intuition, however compelling, didn't match the experiments. Let's get specific. Take two electrons, create them in a special way so they're entangled, their quantum states are linked. Now separate them, send one to New York, one to Tokyo, miles apart, light years apart if you want. Now measure the spin of the New York electron. You get up instantly, and I mean instantly, not after a light speed delay. The Tokyo electron's spin becomes down. Einstein hated this. Spooky action at a distance, he called it mockingly. How can measuring one particle instantly affect another particle across the universe? His answer: it doesn't. The particles already knew what their spins would be, hidden variables. The Tokyo electron was always going to be down when measured. The measurement just revealed what was already decided. But here's where John Bell entered the story. Bell asked a simple question: if hidden variables exist, what predictions can we make? And he found something shocking. He derived an inequality, Bell's inequality, that any local hidden variable theory must obey. Then he compared it to quantum mechanics predictions, and they were different. This is huge. This means you can do an actual experiment. You can test whether the universe has hidden variables or not. The experiments were done over and over, with photons, electrons, atoms. The results were unambiguous. Bell's inequality was violated. Quantum mechanics was right. Einstein was wrong. But what does this actually mean? It means you have to give up something fundamental, either locality or realism. Pick your poison. Locality means nothing travels faster than light. If I do something here, it can't instantly affect something there. Cause and effect are separated by distance and time. Realism means objects have definite properties before you measure them. A coin is heads or tails even if you don't look. The moon exists even when you're not watching. Bell's theorem says you can't have both. At least one must be false. Most physicists give up realism. They say particles don't have definite properties until measured. The electron's spin isn't up or down before measurement. It's genuinely undecided. The act of measurement forces reality to choose. But this creates the measurement problem. What counts as a measurement? When does the choice happen? Does consciousness play a role? Nobody knows. Some physicists give up locality instead. They accept that entangled particles can influence each other instantly across space, but they add a caveat: you can't use this to send information faster than light. So causality is safe, even if locality isn't. Feynman was brutally honest about this in his lectures. He said quantum mechanics works, the predictions are correct to absurd precision, but what it means, what's really happening, remains mysterious. Let me give you an analogy. You and a friend each have a box. Inside each box is a light that randomly flashes red or blue. But here's the rule: whenever you open your box and see red, your friend opens theirs and sees blue, always, no exceptions. Classically, this is easy. The boxes agreed beforehand which would be red and which would be blue, hidden variables. But now add a twist. Each box has a dial with 3 settings, A, B, and C. You choose a setting before opening, and the correlation between your result and your friend's result depends on which settings you both chose. Bell showed that if hidden variables exist, the correlations must obey certain limits. But quantum mechanics predicts correlations that exceed those limits, and experiments confirm quantum mechanics wins. The boxes don't agree beforehand. They can't, because the setting you choose affects not just your result, but your friend's result, even though your friend's box is too far away to receive any signal from yours in time. The universe is doing something impossible, and it's doing it constantly. Now let's talk about what this means practically. Quantum entanglement isn't just philosophy, it's technology. Quantum cryptography uses entangled photons to create unbreakable encryption. If someone tries to eavesdrop, they disturb the entanglement, and you know immediately it's already being used by banks and governments. Quantum teleportation, not Star Trek teleportation, but information teleportation, uses entanglement to transfer quantum states from one location to another. We've done this with photons, atoms, even small molecules. Quantum computers use entanglement to process information in ways classical computers can't. Google's quantum computer solved a problem in minutes that would take a classical supercomputer thousands of years. All of this works because the universe isn't locally real, because particles can be connected in ways that defy common sense. In his lectures on quantum mechanics, Feynman said, "I think I can safely say that nobody understands quantum mechanics." He wasn't exaggerating. We have the math, we have the experiments, we have the technology, but do we understand what entanglement actually is? No. Some interpretations say particles are connected through hidden dimensions. Some say the universe splits into parallel branches. None of these explanations feel satisfying, because they're trying to fit quantum behavior into classical language, and quantum behavior doesn't fit. Here's what we know for certain. Reality is not what it seems. Objects don't have definite properties waiting to be discovered. Measurement doesn't just reveal, it creates. And separation in space doesn't mean separation in quantum state. Let's bring this back to you. Right now, there are particles in your body that are entangled with particles elsewhere in the universe. Not many, not strongly, but they exist. Every photon of sunlight that hits your skin was once entangled with another photon. Every electron in your cells was born in a quantum process that created entanglement. You are quantum connected to the cosmos, not metaphorically, literally. And here's the beautiful, terrifying part. This isn't mysticism, this is physics. This is the experimentally verified structure of reality. Einstein spent the last decades of his life trying to prove quantum mechanics wrong. He died in 1955, believing he had found a fatal flaw. 9 years later, Bell proved the flaw could be tested, and the test showed Einstein's intuition was wrong. His beautiful, reasonable, common-sense vision of reality, objects with definite properties, causes preceding effects, nothing traveling faster than light, was incomplete. The universe is stranger than Einstein imagined, and it's stranger than most people can imagine. But here's what Feynman would say: don't ask what it means, ask what it does. Ask what happens when you do an experiment. Quantum entanglement does something. It violates Bell's inequality. It enables quantum cryptography. It powers quantum computers. It exists whether it makes sense or not. The universe doesn't owe you an explanation that fits your intuition. Your intuition evolved to avoid predators and find food, not to understand the quantum realm. Go outside. Look at the stars. The light from those stars is made of photons. And some of those photons are still entangled with photons that went in the opposite direction when the star emitted them. You're seeing half of an entangled pair. The other half is flying through space, billions of miles away, and somehow, impossibly, those two photons remain connected. Einstein called it spooky. He was right about that part. But spooky doesn't mean wrong. It just means the universe is deeper and stranger than we ever expected. And we figured it out anyway. With experiments, with math, with the courage to accept that our intuitions might be lies. That's the real miracle. Not that the universe is weird, but that we can know how weird it is.